This is AP Calculus BC. We're on lesson 4-7. I changed it to 4-7.1 because I realized 4-7 needs to be broken into two parts. One dealing with the kind of the algebra of the situation, and then a second lesson dealing with the calculus on that algebra. So yeah, today's date is Thursday, April 16th, 2020. I realize that you guys might be watching this a day later or a year later, depending on how into the future we're actually using this video. But yeah, so we're just dealing with partial fractions. Notice it doesn't say anything like integration using partial fractions. I'm focusing on the algebra, not the calculus. So our objective today is to decompose fractions, which is another way of saying use partial fractions, so that we can take their integral more easily in the next lesson. Why? Why do we need to do something to make it more easy? Why do we need to learn a new trick? Because of a problem like this, try it. It doesn't work. Every single time that you see an integral, you always assume taxman. So let's go ahead and try it, and I'll show you why it doesn't work. So with taxman, we assume u is, typically it's going to be the more complex thing. So that's the closest we've got. 2x squared minus 5x plus 3. Now, even if you choose u to be x minus 5, it'll definitely not work. But at least this will get us close. Taxman is going to be the x minus 5. And then u prime, the derivative of this u up here, is 4x minus 5, which is really close. They don't cancel out though. I'm paying taxman a variable rate. Taxman has failed. So what's the goal? What's the strategy to solve this type of problem? And the general idea is break it into two integrals. One integral plus another integral where I have fractions. If I can somehow factor the denominator, those factors are going to go in each of these spots with just some number up here. So think of this as I'm totally making up something about like x minus 1 or something like that, but just some sort of linear factor. If I have that, then I can always take the antiderivative, because if this is some constant x with no squared or anything in it, just some x, and then dot dot dot, and this is some x dot dot dot, it might be 2x or 3x, some constant times an x, but you will always be able to use taxman for these automatically. Like, it unlocks the power to take the antiderivative without any more tricks. It's a one-shot recipe. So how are we going to do that? And again, I'm not going to be writing any more integrals for the rest of the lesson. I am purely just focusing on the algebra that is typically taught in pre-calculus, so it works out well for this class, right? So expand using partial fractions. How are we going to do that? First, I need to factor the denominator. That's always your first step. So maybe I should be writing the procedure off to the side. Step one is to factor the denominator. Nator. I know typically I write out the procedure, but I'm kind of doing this lesson fast and furious. So let's go ahead and do a ninja star. I don't want to use the room up there for writing the steps, so we need an advanced ninja star because our leading coefficient here is 2 and it's not 1. If it was 1, I could just use a normal ninja star. So let's set up this advanced ninja star, and I'm realizing there's a typo. I meant to copy down the same exact question, but I forgot to write that 5. So sorry, please change that now. That was a horrible 5. Please copy down that same problem now. It should be minus 5x, otherwise it can't be factored and we're really, really stuck. And if that's the case, you have to do a really, really hard trick that isn't taught in this class. So 2x and 2x in the top left and top right. You're going to do 2 times 3 in the top of our ninja star, which is going to be 6. In the bottom of our ninja star, we have negative 5, not negative 1, because I miswrote down the problem. And the question is, what times what is 6 and also adds to negative 5? 1 and 6, maybe. Will 1 and 6 work? That would make negative 6. Oh no, a negative times a positive doesn't get us to a positive. So try another one. Let's try 2 and 3. That might work. So if they're both negative, that adds up to negative 5 and multiplies to positive 6. Okay, perfect. So that's the correct way to break it down. And again, treat this as a fraction. So this reduces as a fraction of x over negative 1. Can't reduce that fraction. So let me go ahead and write this with the denominator factored. So x minus 5 is still in the numerator. The denominator now is x minus 1 from our advanced ninja star, and the other side of the advanced ninja star is 2. Oh, that was a wonky looking 2. 2x minus 3. Okay, why is that important? Because each of these factors are going to be the denominator of our fractions. So this is kind of the key step. We're going to say this now needs to be broken into those two pieces, a fraction plus a fraction, where each of those denominators is one of those factors. And it doesn't matter the order that you do it. I'm just doing x minus 1 and 2x minus 3 because that's how I wrote it, but it doesn't matter. And I just want some number up there. So let's create a variable that represents that number, and I'll solve for that variable later. A and a different variable up here, they're not going to be the same number, a and b. That's kind of the key step, and now we just have to do a bunch of different algebra tricks that you have already seen before, but maybe with a few more tricks sprinkled in here and there. So how are we going to do this? How are we going to solve it? The first step is I want to combine like terms on the right. I want to add those two fractions together, and in order to do that I need like denominators. These denominators are obviously not the same, so in order to get them the same I'm going to multiply this top left fraction by this 2x minus 3. So I'm multiplying 2x minus 3, and I can't just do that, I have to do 2x minus 3 in the denominator as well. And similarly, this right hand side is going to be times x minus 1 all over x minus 1. When I do that, that is now going to be equal to a times 2x minus 3 plus, I guess I should do the plus a little bit lower because I have a fraction, right? Plus b times x minus 1. What do we have in the denominator? The exact same thing. I have x minus 1 times this 2x minus 3 and this x minus 1 times 2x minus 3. And you can even see this is exactly the same as before. Like if I were to start simplifying this, I could cross out this 2x minus 3. That's just a over x minus 1. That's exactly what we start with. So everything makes sense up to this point. And the cool thing now is let's go ahead and set this what it was originally equal to. Maybe I can move this stuff a little bit more to the right. Let me grab all that, move you to the right, and let's go ahead and grab my pen yet again. Yes, okay. Still getting used to the program. So I'm going to rewrite this to the left. I have x minus 5 all over 2x. I should really be writing over x to, oh my gosh. Sorry, x minus 1 times 2x minus 3. And we can see really what I can do is I can extend that line and they're the same fraction. This is the same fraction. It's just one giant fraction, a times 2x minus 3 plus b times x minus 1. All of that over x minus 1 times 2x minus 3. So what I'm trying to say here is the denominators are the exact same on the left-hand side and the right-hand side. What that means is I can go ahead and ignore them since those are already equal. The only things that need to be set equal to each other to balance this are the tops, the numerators. So that's what I'm going to do. I'm going to go ahead and write down just the numerators in an equation. So again, the numerator, I had x minus 5 on the left-hand side, and on the right-hand side I have a times 2x minus 3, and then plus b times x minus 1. So from there, I need to solve, and this is probably where most people get stuck. Like, how are we going to solve? And let me show you a quick way to do this. There is a mathematical way to do this where you use elimination or substitution, and it's kind of hard. I'll show you the faster method. If you want to see the other method, it's very useful. It's just a little bit slower. Choose a number that makes this 0 or this 0. You're going to have to do both of them eventually unless you are using even more tricks than I'm showing you. So hey, if I choose that x right here to be 1, this entire quantity is 0. So let's go ahead and try it out. So I'm going to say x is equal to 0. Well, 1. I said 1. 1. If that happens, then my new equation will be, the left-hand side will be 1 minus 5 is equal to a times 2 times 1, which I guess is just 2, minus 3, plus all of that is 0. That's the whole point, right? 1 minus 1 is 0, 0 times b is 0, so plus nothing. And then it's a nice easy equation. So I have negative 4 on the left is equal to negative a, and therefore a is equal to 4. And we have solved for half of the problem. Let's choose another nice value. So let's choose something that'll make this 0. It's a little bit harder to do, but if I choose 1.5, if I double 1.5, I'll get 3, and then 3 minus 3 is 0. So I'm going to say, what happens if x is equal to 1.5? Then the following thing happens. My equation becomes 1.5 minus 5 is equal to, and then b is going to be, sorry, so this whole thing is gone now, right? That's 0, so it's going to be b times 1.5 minus 1, and then from there I'll get negative 3.5 is equal to 0.5 b, and I'm going to double both sides, times 2 on this side, times 2 on this side, and I get negative 7 is equal to b. So I'm basically done. I know what my b value is, so let me go ahead and rewrite this whole thing. My final answer, let's do that in red. So x minus 5 all over this 2x squared minus 5x plus 3. This breaks down as, so our a over x minus 1, so it's going to be, our a is 4, so 4 over x minus 1 plus, and then our b is negative 7, so negative 7 over, and then b was over 2x minus 3, so over 2x minus 3. And I have my final answer. I guess I'll just box the part that we care about that you'll be entering into Khan Academy. Cool. And then theoretically, you can picture what would happen the next lesson. You would think of this as an integral here and an integral here, and then you can actually take the antiderivative. But we're not doing that today. I'm just working on purely doing the partial fractions. Let's try one more final example before you try the homework. Well, I guess we're doing the homework the next day, right? But before you are done, how are we going to use partial fractions? So again, I need to factor this thing. Oh, wait a sec. I should probably write down my steps. There were a lot of steps. Let's try to walk back through. We factored the denominator to, we set equal to a over something plus b over something. And then from there, step 3 is to get, I don't know why I wrote an equal to sign. 3 was to, we multiplied by the other denominator in order to make one fraction. So I'll just say, what should we say? We added, or we, I'll just gonna say make one fraction on the right hand side. I don't know if that's going to be clear enough. You can write whatever makes sense to you. For me, it's going to be make one fraction, and then from there, step 4, solve, and I'll say my hint is find the zeros, or x equal to a number for a 0. Okay, those are our 4 steps, more or less. I might improve that for future years. But here we go. Step number 1, we're going to use ninja star. Just normal ninja star because there's no coefficient in front of the x squared term. So what adds up to 4 that multiplies to 3? Clearly 1 and 3. So this is going to be negative 4x minus 10, still in the numerator, and the denominator is x plus 1 times x plus 3, which means that this is going to be set equal to a over x plus 1 plus b over x plus 3. Then from here, I'm going to multiply a by x minus 3, or x plus 3. I'll just do that in a different color down here. So I really have a times x plus 3, and that's all over x plus 1 times x plus 3, and that's plus b times x plus 1 all over x plus 1 times x plus 3, and I forgot the parentheses back here. All right, so that's looking good. And then adding these two together, kind of the step that I skipped on the last one was the numerators I can add since the denominators are similar, they're like. So I have a times x plus 3 plus b times x plus 1, and parentheses is all over x plus 1 times x plus 3. And remember, what is this thing being set equal to? It was originally equal to this thing. So I'm going to rewrite it again just for the sake of seeing them side by side. This is equal to negative 4x minus 10 all over x plus 1, x plus 3. So since the denominators are the same, we're just going to set the numerators equal to each other. Therefore, I have negative 4x minus 10 should be equal to all of that numerator, which is a times x plus 3 plus b times x plus 1. Alright, so let's find some nice values that make these things 0 to solve. So if x is negative 3, so let's say x is equal to negative 3. If that happens, then I have, this x is also negative 3, so I have negative 3 times negative 4, so 12 minus 10 is equal to, this whole thing is 0, so ignore it. Negative 3 plus 1 is negative 2, so I'll have negative 2b. This over here is just 2. 2 is equal to negative 2b, and then from there, divide both sides by negative 2 to get b is equal to negative 1. Perfect, okay. What's another good number to plug in so that I can get rid of a number? So if I use negative 1, this whole thing will go to 0. So let's say when x is equal to negative 1, the following equation happens. Negative 1 times 4, or sorry, negative 1 times negative 4 is 4, and then 4 minus 10 is negative 6. So on the left-hand side, I have negative 6, and I'm plugging in negative 1, so this x right here is negative 1, plus 3 is 2, so I have 2a. 2a, and then all this term is 0, so ignore it, and therefore a is equal to negative 3. We're done. Go ahead and write down our final answer. I'm just going to go ahead and say our final answer, just rewriting this. I'm not going to rewrite the left-hand side. Our final answer is a, which is negative 3 all over x plus 1, and this is going to be plus negative 1, which is our b over x plus 3. Final answer, and box it. Cool, that concludes notes 4-7.1.